Welcome to the second part for the Pickler combinator paper, which gives us a way to take a value of a type and transform it into a sequence of bits which we can transmit or receive and build back the value. Here we have an example. If we have the value bookmark, which is of type bookmark1, we have b1 is the sequence of a stream. And here, if we launch a stack REPL, we can observe the value b1 as a sequence of bytes, and those are printed as characters. So what you see, like /SOH, is the character which is displayed for the actual byte 0, 1, and /ACK is for 2, etc., etc. Anyway, we could see last time that we had not just the core library, but we also had combinators. And that allows us, when we have some more specific data structure, like here we have a record, a URL, and the record URL has the essential information, those 4 bits of information, which we will encode, we will serialize as a tuple with 4 components. So we're using the quad combinator applied to string, p-maybe-nat, string, which are those 4 things are themselves a Pickler combinator, which are packed together with this higher order combinator quad. And we also have the wrap combinator, which will, upon serializing, which it will extract the information content of our user-defined data structure and make it amenable for the serializer, for the Pickler combinator to transmit. And upon deserialization, we'll have the reverse operation. We'll take the tuple and we will build the value of our specific type. Likewise for list, you can see here we have a bookmarks type, which is a list of bookmark. Now, if we have bookmark, for instance, here which is a either type, we have another combinator, alt, which takes as a first argument a tag function that goes from our specific user-defined type, bookmark, into integer. And that integer will say which of the combinator among the list of combinator which is provided to choose. So if we have a link, it will have the tag 0, and we will pick the first combinator. If we have some value of type folder, we will look at the combinator at index 1, which is the highlighted combinator, which itself is a composed combinator, which will record a tuple and apply back and forth the folder constructor or extractor. We see that when we serialize, we pattern match on folder A and extract the A, which is a tuple, which then can be serialized with the Pickler combinator pair string bookmarks. Now, with that thing, we can serialize, for instance, a value bk, which is a typed list of a bookmark, and we can serialize it as a string, a sequence of characters as displayed below, and we can of course get back the value. We have no type safety. We have to use the correct Pickler when we serialize and when we deserialize. So another example is a lambda term where we have a ternary choice, and the same approach works where we tag the particular value with an index, and we let the high order combinator alt to choose to select which Pickler combinator to apply. It will, upon deserialization, for instance, use the constructor lambda, and upon serialization it will extract the the argument out of a lambda constructor. It's the same strategy. Now, another strategy which can be used is to say, okay, we have a ternary choice and we have a binary a choice already encoded as part of the library, which is p either. So we could try to reconstruct this ternary choice with a sequence of binary choice, which leads us to this combinator. And we can see that this combinator is in one-to-one correspondence with the type. We have either a string or the rest, which is either a lambda or an app. And so there's a one-to-one correspondence between the type and the combinator. And the discrepancy is matched with an external wrap, which says, okay, if you're in the case of left, the sequence of a binary choice is just one step. The case 0, we will apply var, and in the other case we will apply lambda and app to the sequence right left and right right. Now if we apply that to some example, for instance kki, we can see that kki has a lot of sharing because it's constructed with the same value k, and it's a little bit unsatisfying to see that the encoded bit stream has a lot of repetition. If we want to kill off this repetition, we can modify the core Pickler combinator library. But first let's look at an example on what this modified Pickler library will be. So the first combinator URL and bookmark are the same, and here we're just looking at the list, member list, which will try to kill off some repetition inside of a list. And we can see that in action if we take this value bRepeat. And when we look at our original Pickler, we had a lot of repetition in the encoding, whereas when we look at our new combinator, it has a minimal amount of repetition. That is, it has /SOH, which is 111, which basically says, go look at first value which you've serialized. And of course we can get back the original value. Now let's look at what has changed inside our core library. So I will put above the old version and below the new version. So in the new version we have some extra state in our st type. That is, the state is not only the big stream, which is the first component, but it has some extra state, s. The pickle has an extra argument, s, which is passed on to the app p component of the Pickler. But apart from that, nothing has changed. We just pass on the state wherever it needs to be for pickle and unpickle. Likewise for lift has stayed the same. Remember that lift, since it encodes the presence of the value x as part of the format, when we write lift, we do not write anything inside of the bit stream, and when we read, we do not care what's in there. We insert the x, which has been given to us because it's been encoded as part of the format. Now sec is the most interesting part. It's still the same signature as before, and we apply the same procedure. We extract from B, we extract some partial information A. With that partial information A, we select a specialized Pickler for B, PB, and the tricky part is the touchy part is here. So we still want to have A ahead of the stream, right? When we decode the stream, we want A to come first, because that's what will allow us to select the specialized Pickler for B. So we write A using the Pickler PA, using this state, this pair of bitstream and state. So the state here is S, because upon decoding we will want the state S, the original state S. and we will write the A. Now, what is this CS prime prime? The CS prime prime, which we use, comes from writing B with the specialized pickler PB. But it comes from writing with B with the state S prime which we had from writing A. So although we write A first, we put the result of writing A after the result of writing B, or said in another way, it will appear before when we read it. But this notion of state is important, and as a result we give the complete sequence of bits CS prime and the final state, which is retrieved after writing B with a specialized pickler PB, and this will be the encoding part. Now to decode, we will of course take the state S and decode A with the pickler PA, which has been provided. Now using that state S prime and using the pickler, the specialized pickler providing by K at the value A, we will decode the value of B. This is not enough for writing our memo list. We will have to go into this extended library. We can see that memo list uses memo fixed list, which uses Tokenize. So Tokenize takes a pickler, and it also has some extra argument, which is a dictionary. And the way it works is that, as usual, we will try to extract some partial information. So we use seek to start with. And the partial information that we will look specifically for is, do we already know this X that is required to serialize? And if we found it, we will yield back some position, n-1. And if we do not find it, we will give 0. So we will store this partial information, n-1 or n-I or 0, and with the special meaning that if we have seen something if we have 0, we know that we didn't find it, and which meant that we had to use the pickler P. And if we have found it, we can just look up in our dictionary, which is part of, in a way, the static part. Everything which is on the left of something which builds a pickler is kind of a static thing. So we just look up in the dictionary, and we use lift to just put this value inside of the stream. Although there is no relevant information, there is no information inside of the stream, we know by the format and by the pickler that we have to put the content of the dictionary at the index n-1, n-I. So there is a little bit of content in the stream, which is the position I. And so this tokenized version, it works for any pickler. It's just a generic way of making things more efficient. And now memo fixed list is a very natural use of Tokenize. So we are trying to serialize a list of fixed size. So if we know the size is 0, it's part of the left side of this pickler PAUS, right? It's part of the thing that allows us to build us a pickler. So we describe a format. So if we know statically in our description that the list that we're intending to read is 0, of length 0, we can just left the empty list and do not read or write the stream. We just shove empty list inside of the constructed value as a result. Now, if we have some list of lengths n, we can start with the usual strategy of getting partial information, in this case just the head position in the list, and use the optimized pickler, which will store the actual value or a reference to the value. Once this is stored, we have to give a parameterized pickler, parameterized by the value x, which we have extracted, which comes from the head, and this will be the parameterized pickler. And which pickler will we use, given that we have x in our context? Well, we will apply the same strategy. We will project out some partial information, which is the tail, and we will store the tail with the particular pickler that we are building with two extra things. First, we encode the static, in a way, knowledge that the fixed size of the list would be n-1, and we will also enrich this dictionary with the value x. We will say, don't worry, for x we've already put in we've already serialized it, so it's part of your vocabulary. You can make a reference to it. You can use lift at this index to make a reference to it. And once we have taken this partial information out, we can continue with xs and use lift x followed by xs as the final pickler. Now, memolist is the composition of such function. So it does seek length nat to extract the partial information about this list, which is the length, and it's composed with memo fixed list dict. So it's not always easy to see how those things compose. So if we write the type of memo fixed list dict, we can see it's the first part, and the second part, sec list nat, is a function from this type, int pu blah 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 to pu list of a s. And since we're using compose, the middle part goes away in a sense. We can compose and we just see the input and the final output, and that gives us back a function of this type, puas, pu list of a s. And here we see that we have dict of type list of a as an extra parameter, which is the context for the whole computation. So we can use this optimized version of a list to build picklers with memory, and that's exactly what we're doing here. When we use SB2, you can see that we have the first part is the encoding of the value, and basically what follows is just the same value over and over again, because we've encoded as part of the format that you can make a reference to what's before, and so here it just gives always the same reference. So upon decoding, it will look up the dictionary which is built dynamically and give us back the value. And we have the same problem of type and safety, where we apply a different pickler for encoding and decoding. We will have an error, a runtime error, not a type error. Now that was for list, but if we look at lambda expression, we have this strange constructor, strange combinator share, and if we look at the implementation, it's calling use state with add, which is what we were using before in the memo fixed list to enrich the dictionary, and it uses some function from dict to tokenize dict p. So it's using some pickler parameterized by this dictionary, which is this state basically. And that's exactly what we were doing with Tokenize dict PA. We are, the context gives us some dictionary, and we are building this specialized, more efficient pickler. So user state add and this and dict this function is just a way of generalizing this all those steps that we were doing before. So if we look at user state inside the core pickle, we see that it takes an update function and a select function, and it builds a new pickler out of those two arguments. It builds a pickler, an unconditional pickler, which gets the state, select the pickler, apply it at the current state with the current stream, and gives back the new stream with the updated state. And the same for decoding. So as a result, we have basically the same pickler that we had before, except we have this outer tag, extra high order function that will optimize and build the dictionary as we go. And so the example on this value kki will be a very instructive. It will give us a compressed version, and in order to view exactly what it does, there's some depiction here. So if we convert the character to int, this is what we get out. And to understand why we have such value, the dictionary which is built will build terms at those index, like 1 will denote var x, 2 will denote this whole expression, 3 this expression, 6 the entire expression, etc., etc. And so if we follow the value which are output, we see that we are following the structure. And there's more detail in the paper. Not much. But here is what we had before without the compression, and actually with a little mistake because it was x. So here is what we had before, and we can see that this part, for instance, is not repeated. The part var x, so the sequence 0, 1, x, and likewise the command part k, which existed in the term, is not repeated. So it will stand for 1, 1, x, 1, 1, y, 0, 1, x, and that's repeated in the first part. And instead of repeating it, we just put a 3 to make a reference. Now this is the paper functional Perl, and as a reference there's an interesting mention of embedded interpreter, which looks like a very interesting paper. A circular program by Richard Bird. This is the repmin construction, which works for lazy language. If you want to make multiple traversal, computation that would depend on multiple traversal but don't really need multiple traversal. Like if you get a tree and you want to transform every leaf of the tree with the minimum value of the tree. So instead of first calculating the min, which requires traversal, and then building a tree out of from structural recursion, which would require another traversal, you just build the whole thing in one go. It's a beautiful technique. And it's worth to mention this book, ML for the Working Programmer, where there is a great example of parser combinator. It's in one page. It's beautiful. It's in the ML or SML or camel. This paper looks very good as well, embedding an interpreted language using higher order functions. And of course, this is a classic, How to Replace Failure by a List of Success by Mr. Wadler, which talks at great lengths about monads, if I remember well. So I hope it was instructive. If you have things that you want to see, if you liked some stuff, if you didn't like some stuff in this video, do not hesitate to say so, and see you around.